Right, so let's look a little bit at lattice cryptography, and we'll focus in on ring learning with errors key exchange. So the problem that we have is that many of the existing methods, including RSA, elliptic curve, Diffie-Hellman, and L-Gamma, will be broken, or the security will be severely reduced with the advent of quantum computers. The basic core methods that they're based on will not become a hard problem in the face of quantum computers. So we need to very quickly move away from our existing methods and move towards a quantum robust crypto methods. The four classifications of them are lattice cryptography, and in this presentation I'll give you an outline of what lattice cryptography looks like. We have traditional code-based cryptography, and that's based on things like linear codes, such as error-correcting codes. We have multivariate polynomial cryptography, and also hash-based signatures, where it's possible for us to create one-time signatures using a hash of our message. Okay, so what's public key? Okay, so with public key, what we have is that we have Bob, and we also have Alice. Okay, so we have our private key, that's a secret key, and we'll call that private. And over here, we have a private key. And then what we do is we have a public key for Bob and another one for Alice. And these two keys work together in that you can encrypt with one and decrypt with the other. Doesn't matter which way around it is. So in most applications, we use this in terms of key exchange and also in digital signing. We normally use symmetric key encryption, such as AES, for our core encryption of data. But we use public key encryption in terms of signing a hash of the message, and also for key exchange. So if we have, say, some data, then we often take a hash of the data. And then what we do is that we take the private key of Bob and encrypt that hash. That then gets sent over. Alice checks the message and then takes a hash of the message and then decrypts the signed hash that Bob sent with Bob's trusted public key. If she agrees to the hash that she receives by taking a hash of the message and also from Bob, then she knows that it was Bob's private key that actually signed the hash. The other way that we can use public key encryption is within a key exchange. And what we really want to do is to create a secret here for Bob, secret for Alice. They then do some sort of calculation and send a value over, and then at the end of it they have the same shared key. Most of our existing methods are based on the Diffie-Hellman method, typically using discrete logs, g to the power of x, or are using elliptic curve methods, where we use a base point and then we have a secret or private key value, which is a value which adds the points together. But unfortunately, as I said, that method needs to go, because with quantum computers, then that doesn't become a difficult problem anymore, and all our data and all our signing could be cracked. So let's look at lattice methods. So with a lattice method, what we have is that, and I'll just draw it in 2 dimensions, but typically we might have hundreds of dimensions. It's rather difficult for me to create that. So I'll just do our lattice in 2 dimensions. So if I take a point, let's say 2, 0, and I'll take another point and I'll make it 0, 2, just to keep it easy. Okay, so we can have another point here, and if we call this vector 1, I can create a vector here. So let's create that vector, and I can have another vector here using the origin as one pointed vector, and we have another vector v2. I can now create another vector which is v1 plus v2. Okay, remember vectors look a bit like that. So we add them together, so we add the x. So we take 0, 2 and 2 and add 2, 0 and get 2, 2 there. Okay, so I can have another vector at 4, 2, if this is 4, and this vector here will be 2v1 plus v2 as a vector. I can now go ahead and I can create my lattice, which will look a bit like this. Okay, so that will become our lattice, and all the points on that lattice will make up our lattice grid. Then what we have is we have these vectors which will point to a point on the lattice. What we have with lattice cryptography is that we create a point on the lattice, and then we introduce some form of error to give us a new point. So this gives us a new vector, and the challenge is then to find the closest vector to the point that we actually have. So while that looks quite easy when we have quite a small lattice, just in 2 dimensions here, when we have a multi-dimensional lattice, it is actually quite difficult to find that point, the original point, without the error that we're adding. Also, there are possibilities for other vectors, but we find the closest vector to the origin. Okay, so it's this method that we use which gives us a hard problem to solve if we don't know some of the secrets involved. Okay, so here is our simple lattice. As I said, there's 2, 0 and there's 0, 2. There's our first vector here. There's another vector here, and here are all the points on the vector, on the lattice. Now if we introduce a small error as a vector, we end up with this new vector. So the nearest, the closest vector problem is to find the closest vector to that one on the grid. We can also take 3, 2, so 3, 2 and 5, -1, and that will produce this type of lattice. So a lattice you'll typically see in lines like this and like that. That makes up our lattice. Okay, so you can draw your own lattice if you want. Okay, so if I pick a point, let's say 4 and 3, let's draw that as a lattice. There we go. Okay, so let's go for 10, 0. So we should have a point down here somewhere. There it's there, there's 10, 20, 30, and so on. Okay, so in this way we can actually draw our own lattices, but remember this is only in 2 dimensions, where a more complex lattice would have many dimensions. Okay, so let's initially look at a technique called learning with errors. With learning with errors, we take, in this case, a matrix A, and we take a secret matrix S, and then also an error matrix. So the example I've used here is based on the example from this summer school here, so you can actually go and check out the numbers, but I'll try and illustrate it with some Python code. Okay, so here we go. This is a 2-dimensional matrix here, and the Z means integers. We're only dealing with integers. This defines the ring that we're going to use. So this is a prime number, and we're taking 13 as a prime number. If we use a prime number, everything becomes mod. So we mod all of our numbers with 13. So the values we get will be 0, 1, 2, up to 12, and then it goes round again. That's the ring that we have. And the good thing with these rings is that all of the math still works, even though we're doing mod of the prime number each time. In real life, we would be using an extremely large prime number, such as one with 1024 bits. Okay, so we'll start off with a 2-dimensional matrix. We'll take a secret, so that's a 7 by 4, 4 by 1, and then we have a 7 by 1 result here. The challenge for someone is to be able to look at these 2 values and to try and work out what the secret actually is, the red bit in there. Okay, if we weren't to use an error, then it's actually quite easy for us to be able to determine these values from Gaussian elimination. But an improved method, and something that's a hard problem, is to introduce a small piece of noise. So if we look at previous one, 7, 8, 1, 10, 4, 12, 9. Now, if we add on a small amount of noise or an error each time, so it's 24, we multiply them, and then we add that, and we should get that. So in this case, it's actually difficult to work out what the error actually is if we have this and we have this to recover back the secret when there is noise in there. But obviously what we'll have to do eventually is to get rid of the noise. Okay, so here's an example here, and we're using NumPy in Python and setting up our 2D array there, and we'll make sure that all our operations are done with a prime number of 13 or mod 13. Okay, so when we multiply an array, so it's that times that, that times that, that times that, that times that, plus that should give us our result. Then we do that times that, that times that, times that, that times that, plus that. Okay, so that will give us our result here as a matrix. So our 7 by 4 and then our 4 by 1 becomes a 7 by 1 and as a result. Okay, so here is our definitions in Python. Okay, and if we do the calculations, then we end up with this here. So that times that, that times that, that times that, that times that, plus that gives us that mod 13. Okay, so everything is done mod 13 from them. So can you see here, there is the matrix multiplication, and there is the addition of the error here. And when we do the mod 13, it takes all the elements of the matrix and we'll do the mod 13. So we end up with a value of 15, then that becomes a value of 2. Okay, so when we run it, hopefully we'll get this answer here, which gives us our basic solution for that. Okay, so now let's look at a real example, and it's ring learning with errors with key exchange. Okay, so with ring learning with errors, we start off with a polynomial. So this is a bit like having our vector, but it's only we've defined it here as a polynomial value. Okay, so we're taking Z13. Rather than do the, if you have polynomials, rather than doing the mod of the prime number, we divide by the highest value that we have, which is actually, this is 0, 1, 2, this is 1, 2, 3, 4. We divide by x to the 4 plus 1. And that creates our ring for us, so we never get a higher value than x to the power of 3. So in this case, we take a random value, we multiply, we create our own random polynomial here, and we'll multiply the two of them together. Then we take that polynomial and add some noise, and we get a result here. So even though we have this and we have this, it is not possible for us to determine the secret here, or it's very difficult for us to do that. So here we are. So let's say that we take the value of A here. We take our secret value, and then we take some error value here. Okay, and we create our calculations. So there is A. This is A times the, this is the secret value here, secret value, and this is the error for A. And we work out this value here, which is this value. Okay, so this is A, SA, and EA gives us this result. We then divide by this. In Python, we represent that value by that, and we do a divide on the polynomial, and it gives us a ring. So we never get a value greater than x to the 3 in this case, because obviously when we multiply x to the 3 and x to the 3, we get x to the 9, we get x to the 6. So we need to get back into x to the 3. Okay, so here's our little bit of code. There's our A value. We're going to multiply it by the secret value. So this is this operation here. We can then divide it by this, create a ring. We'll then add here our error, and then this gives us our result in here. Okay, so that's the basic steps that we take for ring learning with errors. So let's look at ring learning with errors key exchange. Okay, so Alice generates her polynomial and shares it with Bob. Then she takes her secret, multiplies it with this polynomial value, and then does the add with her errors. Bob does the same on his side. He'll create the polynomial A. They both share A as a polynomial. Bob has a secret that's like his private key, and Alice has her secret. And then Bob will create his own error value, and then they will then exchange these values and then hopefully end up with the same shared key in the end. So here is the result of that. So Alice receives this value here, then she multiplies it with her secret value. Bob will receive Alice's value and then multiply it by his secret value. Okay, so that's how the calculation works. So here it is here illustrated. They share the polynomial, random polynomial. Alice generates her secret, Bob generates his secret. So this could be for every connection that they have. They create a new shared secret. All they want to do is to create the same shared key in the end. So Alice takes A, multiplies her polynomial by A, and then creates a random error polynomial A, and then works that value out. Bob does the same on his side with his own secret and with his own error value. They pass it over, and in the end she multiplies it back with her secret, and Bob does that then. We end up with S A S B A plus E B S A, and then over here S A S B A plus E A S B. This is defined as the noise or the error value. We then look at probabilistic encryption to be able to resolve that error back to what it should be. So I'll show you the example here. So here's the code that we use for the probabilistic part of this. So we look at the values that we create, and then if the value is between q upon 4, then we define that as a 0. If it's between q upon 4 and q upon 2, it's a 1. So most of the time our value will be fairly well, the noise will be much smaller than the overall value, and we'll be able to pick off our value well. If the noise begins to grow, if we keep calculating these values, then the noise values will grow and we can end up with errors in this. Then between Q, 3Q and 4Q, we define it as a 0. And between 3Q over 4 and Q, we define that as a 1. So this allows us to then resolve the noise back into the zeros and ones, because what we do is we really encrypt each bit one at a time. So let's see if we can look at the code for this. So here's an example here. So let's say I use powers of 11. There we go. So there's the same shared key at the bottom there. This is our A. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so that gives us the powers of the polynomial. And the Q value will give us the maximum value for those polynomials. So a value of 10 gives us 2 to the power of 10, which is 1024. And that's the value that's worked out here. We can increase the values, such as to 2 to the power of 12. So we see our values are increasing here. In real life, obviously, we'd use fairly large values for that. But we'll just drop that back down to 10 there. Okay, so here is Alice's secret polynomial. Here is her error values. And then the secret multiplied by the A plus E gives us this. Okay, and the same with Bob. Bob's secret, that's his private key, that's his errors, and that's the values he gets. So they'll send that over, and then these are the values that we then calculate from that last little calculation that we saw. And there we are there for Bob. We then go into this noise reduction to use the probabilistic encryption to be able to get rid of the errors and end up with the same shared key. So the Python code is here. It's just me generating a polynomial of a certain size, a random one. This is the code that we saw before. Notice that everything is done mod Q. Q is 2 to the power of the value here. And then when we get to the noise threshold, here are the thresholds being applied to be able to resolve back our bits as a 0 and a 1. Okay, so in the end we should end up with the same shared key. Okay, and with this as I said, we use a single bit at a time and resolve that. With the ring-len and with errors, we encrypt a single bit and then we try to recover that bit back once we've removed the noise or the errors from it. Okay, so that's given you a basic introduction to lattice cryptography, and we've been able to see ring learning with errors key exchange as a post-quantum or a quantum robust cryptography method. The great advantage with some of these methods is that we can use homomorphic encryption on them. We can encrypt A with a key, we can encrypt B with a key, and then when we operate, we can operate to determine the encrypted value of A plus B without finding the value of A plus B, and then when we decrypt, we can actually get A plus B back again, and that gives us our homomorphic encryption methods. Okay, thank you.